Yeah, so getting NTFQs. So it's generally natural to natural, and the way usually NTFQs look like is we have some function f, and we're given a condition that f of something 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 divides f of something something something, and then you want to find what f is. Another trope that comes up is that you are given f of something something is similar to f of something else in where similarity is defined by the problem. Like it might be number of bits in these numbers, or it might be in the number of divisors that each number has. So like in the first type, usually in such NTFQs you are not constrained because you don't have equalities in both the cases. So in the first type, you might constrain it by making this side a prime, or having making it have few divisors, or maybe even one. In this case, two theorems help out a lot. The first is CRT, and the second is Dirichlet's. So Dirichlet is basically that if you have some arithmetic sequence like a n plus b, and GCD of a comma b is 1, then this sequence has infinitely many primes. So for example, 4n plus 1 has infinity number of primes. 6n plus 5 has infinity number of primes. And you can use this with CRT in the way that uh, say you want to find a prime which satisfies some conditions, some modular conditions. Like you want a prime that satisfies 1 mod 5. It is also 3 mod 7. So by CRT you can find an arithmetic progression that is in this case what is it? 5, 6, 21, 26, 31. Yeah. So 31 mod 35. So P has to be 31 mod 35, and we can find the prime P such that it lies in this AP. And then you can choose such a P. You can choose infinitely many such P. So is this clear? Okay, I'll take that as a yes. In this type of functional equation, you have to be a bit more creative. So, say for example, you're asked the number of you're told that the number of bits in both these quantities are equal. So again, you want to constrain it. So you might make one of the LHS 2 raised to n, so that it has only one bit. If the question is about both the sides having the same number of divisors, you might make one of the sides a prime or a prime power, so that you have a lot of control on the number of divisors. So that's one thing you do. Another thing that you often do is induction, because n to n is like really nice with induction. So you might be able to find f of 1 very quickly, and then you might be able to find all f of primes quite quickly, and then maybe you can fill in the stuff in between. So yeah, that's most of the strokes you might see. We'll take any problem.
It already started.
Yeah. So try scrolling for some time. and then we can discuss the solution. Is the problem statement clear?
There's a question in chat. What is a
Excuse
complete
me.
residue system modulo P?
Sorry, I can't hear you.
There's a question in chat. What is a complete residue system modulo P?
Should probably let me shout. Yeah, so basically, complete residue module P is that it just means that x comma f of x, these elements leave the remainders 0, 1, 2, 3 minus 1 when divided by p. Like uh, 1 comma 3 comma 5 is 0 comma 1 comma 2 when divided by 3, right? So this is a complete modulo set mod 3. So the question is saying that this set is a complete it takes all remainders when divided by p. Is this clear? Yeah. What do you mean by CRT for each case? Oh, so basically over here we just use CRT to compile these two pieces of information into one single piece of information. Like we wanted to find a prime P such that it is congruent to 1 mod 5 and 3 mod 7. So we use CRT to make that 31 mod 35, and then we used Dirichlet's theorem to say that there are infinitely number of primes which are in the AP 35n plus 32. And all such primes will leave a remainder 31 when divided by 35. So they will leave a remainder 1 when divided by 5 and 3 when divided by 7. By other theorem, you mean Dawkins, right? Mm.
Wait, are we doing the first, which is the first problem?
So
Are we
this
still
is
doing
what.
this?
Yeah, I just gave the problem. So you guys can try for like 10 minutes. Yeah, so will you take a screenshot of this?
Yeah.
Okay. So yeah. So basically, Dirichlet's theorem is that if you have any coprime numbers, a comma b, then you can find an arithmetic sequence an plus b. So for example, if a and b are 3 and 2 respectively, then we have the arithmetic sequence 3n plus 2, which is basically 5, then 8, then 13, then 11, then 14, and so on. And the theorem says that in this sequence, you can find infinitely number of prime numbers. So over here we have 5 as one, we have 11, we have 17, and so on. So there will be infinitely number of primes in this sequence, in any such sequence. Does this make sense? Oh, this can't be proved with elementary means. It's quite a tough thing. Yeah, should I give a hint to the problem? You have it inside.
No, not yet.
Okay, I'll wait until say 33, and then so like you might have guessed f of x equals x plus 1 box, and all I think this is the only solution. Can't do CRT for inclined frames, but you can do it for arbitrarily large frames and arbitrarily large number of frames. I don't know if that's what you mean. Also, I think we should, uh, I'll give a hint for the Indonesia probably. Yeah. So, first things first, there are a lot of F's in this condition, right? Like almost every term is surrounded by an F. So, like, what do you think we should try to prove? Should we prove surjectivity or injectivity? Like, one of them seems quite nice in this.
Surjective is just false if you look at the
Exactly. Since f of x equals x plus 1 does not take, there's no such f of a such that f of a equals 1. So, this surjectivity is not a good idea. And injectivity is really good because suppose we have f of a equals f of b, then all these terms, if we put a in this sequence, this becomes a, f of a, f of a, and so on. And when you put b in this, you get
So then you get
b,
A is congruent
f
to
of
B mod
b.
P for all primes.
Exactly. Yeah, so you get this, and this is this set. One sec. This set is just b, f of a, f of a, and so on. And since these two sets are supposed to be equal, like both of them are supposed to take all remainders and divided by p, A must be congruent to B mod P. A must be congruent to B mod P. Is it clear why this happened? Okay. And now what we do is that if A is congruent to B mod P, we can just like choose any random prime. So we can choose a very, very large prime, which is much bigger than A minus B. And then you'll have to get that A minus B must be 0. Does A equals B? And we have proven injectivity. Did this argument make sense? Okay, good.
But like B should change for every mod P as B is the remainder, no?
Yeah, nice. So, see, we have, did you get that A is common to B mod P? We got
Like
this from this argument.
seeing the we are
But
seeing the mod for a specific prime. So as we change the prime, the mod B should change.
yes, but see, we have A common to B mod P. Thus, P divides A minus B. Now, this part, this is constant regardless of what I choose T to, right?
Yeah.
So, I can T to be something like a million, much bigger than A minus B, and eventually it has to be 0, right?
Will like B change? So it is for
Like,
prime P1 there would be B1, and for a prime P2 there would be B2.
that is the remainder. I'm not talking about remainders. I'm just saying that T divides A minus B. Okay, let me go through this. Okay. So we have that A, f of A, f of f of A, f of T minus 1 of A. Leaves the same remainders as B, f of B, f of B, and so on. However, we have that this is nothing but b f of a, f of a, f of p minus f of, because f of a equals f of p. Does this make sense?
Yeah, I got it.
So since this and this are same, this and this are same, all of them are same. This and this must be same. This and this must be same modulo p. That is, a and b leave the same remainder when divided by p. Sorry, what? A and b leave the same remainder mod p. And this is the same as saying p divides a minus b. So a and b are fixed. So a minus b is fixed. And if a and b are like something like, I don't know, 7 and 3, then this becomes 4. And I can definitely choose like p5, for example, any p greater than 4, such that this is false. So this has to be 0 and a equals b. Did you get this part? Or should I explain it again?
Yeah, I get it.
Oh, so yeah, we've proven injectivity now. Like try and make two of these elements, say fx and f of x, the same remainder, modulo some p. Because that's not possible, right? Because all of them have to be different remainders. So try to force that to happen, or assume for the contradiction that it does happen. So I'll give another hint. Basically, the idea is assume f of x equals x plus c for some c and for some x. Then try to choose a prime p such that this set has to have two common elements, has to have two elements that leave the same remainder.
Like if we choose C, a prime P, which is a divisor of C, wouldn't that work? Like, wouldn't
Correct,
it be a
very
contradiction?
exactly. So because then if p divides c, then x and f of x. This is x and x plus c. These
Wait,
will
then
this remain
aren't we
these
just
remainders x naught. Sorry, go on.
we can just have C is plus or minus 1 then.
Exactly. So that's the only like edge case.
And then for 1, it must be plus 1, and then by injectivity, it must be plus 1 everywhere. So we are done.
Exactly. Exactly. I'll just explain what he said. So we have that if f of x equals let x f of x equals x plus c for some x comma c for some x comma c, then we have the set x comma f of x comma f raised to p minus 1 of x. And if we choose a p such that p divides c, we note that x, we know that f of x leaves the same remainder as x plus c leaves the remainder as x leaves mod p. And this is a contradiction because none of these elements leave equal remainder when divided by p. But that can only happen when there does exist a prime dividing c. And the only place where there does not exist a prime dividing c is when c equals plus minus 1. Is this part clear? Okay, great. So now, so after this, what you do is that can f of can like let's try to find what f of 1 is. F of 1 has to be 1 plus or minus 1. But it can't be 1 minus 1, which is 0, because 0 is not a natural number. It is not a natural number. So it has to be 2. So f of 1 equals 2. And after this, f of 2, there are two choices. It can either be 2 minus 1, which is 1, or 3. Wait, what is the problem with 1? Here. If it is 1, then consider the set 2, f of 2, f of 2, f of p minus 1 of this becomes 2, f of 2 is 1, f of 1 is 1 again, and these two are equal in
No, f
modulo
of
p.
1 is
This is a
2,
contradiction. Oh shit, f of 1 is 2,
but then mod 3
and
again. Yeah, you have a problem.
these two are, these two are the same.
Wait,
So, contradiction.
it doesn't work immediately. I'm not sure. We still have some work left.
नहीं मतलब this is right? 2 and 2 can't be, have to be the same in
Yeah,
modulo p. So
yeah,
it's
yeah.
contradiction. So f of 2 is 3.
And now you can
But
induct. You needed 2 as
sorry,
one more base case. Now you can induct.
exactly. So like just to illustrate the induction, f of 3 can either be 2 or 4, but we had proved injectivity. So 2 and 2, this is not possible. So it has to be 4. And then we can just induct. We can say that f of n is either n minus 1 or n plus 1,
Like
but
this
n
can
minus
also
1.
be approved like from parity induction, like one for odd parity numbers and one for even parity numbers in induction.
Yeah, sure. Yeah,
You don't
just
need.
because fn and ffn minus 2 are what is connected. That's why we needed two base cases. Is this induction thing clear? Should I explain any part of it again? Why f of x has degree 1? Yeah, so basically, wait, yeah. So we assumed we didn't assume it is degree 1 anywhere. We said that let f of x equals x plus c for any x or c, for some particular x or c. And then we said that then consider this set and consider a prime p dividing c if c is greater than 1. Then we have that f of x, this term, and this term have the same parity mod, and that is a contradiction. So that's why we had c equals plus minus. We didn't assume it is linear anywhere. We just assume that c is f of x minus x.
So like, wouldn't there that like if we say that was for a specific x, f of x equal to x plus c. For the other x, let's suppose that it's somewhere somewhat x square plus x plus 16, something like that.
It,
Mm.
Yeah. No, but
So,
see. Yeah. Wait. Sorry. Like
wait, like, I
actually,
guess you can, without introducing c, you can just directly say f of x minus x equals plus or minus 1.
wait. Like c is not a constant. C is not a constant over here. C is just x minus f of it. F of x minus x for
oh,
some x.
okay. I get it.
Sorry, I think I used C, that is why that causes the issue. But C is not a constant. So yeah, basically really the good thing about natural numbers is that you can induct. Like you can't do this induction in reals or even rationals. Induction is kind of tough. So that's why like if you can figure out f of one, try to induct values. Keep that in your mind. Since from f of yeah. Oh, so I think I should get the next problem. Is there any doubt in this? Is C is PT? Yes. Yeah, again, we are not assuming it has a linear coefficient P or not. We're just letting uh wait, I think you meant something different. Wait, can you elaborate on what you mean? If C is PK plus one or minus one? No, like C has some prime divisor, right? Like if C is 10, we can choose P as 5. If C is 12, we can choose P as 4, P as 3. If C is 11, we can choose P as 11. We get to choose P, given a fixed C. Yeah. By the way, that one was Indonesia, TSTST. Uh, yeah, and this is the next question.
Which handout are these from?
No handout. I just took it from your piece.
Oh, okay.
Like this one, for example, is Sophie application 24.
Oh, crazy.
Yeah, I think I should explain the statement. So the first sits again end to end, and it's basically saying that it is loosely increasing. That is like if A is lesser equal to B, if B is greater than or equal to A, then f of B can be equal to f of A, but it is always greater than or equal to f of A. It is not strictly increasing. And we are also given that f of a plus f of b has the same number of divisors as a plus b. Uh, just to make stuff easier, I'll use this notation. F of b is similar to a plus b. Is there any doubt in the problem statement? Yeah, weekly.
F of 1 equals 1 is pretty immediate.
Yeah. So f of n equals n is a solution. Like please like just throw out your ideas when we do. F of x equals cx.
F
F
of
of
one,
x. No, that doesn't work.
uh,
F of
F
x
of
equals
one,
the reason it is sorry one.
no, F of one has to be one. I
Yeah,
think.
you just substitute A equals B
Yeah,
equals
very
C.
good. Very good. So a equals I suppose you did a equals b equals 1. So if you do it a equals b equals 1, we have that f of 1 plus f of 1 has the same number of divisors as 1 plus 1, which is 2. So we have that 2 f of 1. Since this has two divisors, the number, this has to be a prime because nothing else has two divisors. So this is 2. And since 2 divides b, p must be 2. So f of 1 equals p. Good. So yeah, maybe you can try to find f of 2, f of 3, and try to end up or something.
Yeah, F of 2 equals 2 is also obvious. A equals B equals 2.
Wait. So what did you substitute?
A equals B equals 2 gives F of 2 is 2.
So f of 2 plus f of 2 is similar to 2 plus 2 equals 4. This has b of 4. Number of
3
divisors of 4
divisors.
is
3.
3. So we have that 2 f of 2. Since note 3 is a prime, which makes stuff very easy because we know that it has to be of the form p square.
Yeah, exactly.
So, so like this is how you can try to bound. We want b of 4 to be a prime. B of anything on the RHS to be a prime. So maybe you can think about that. Anyways, so 2 divides p square. So p has to be 2. So this has to be 4. So f of 2 is 4 by 2, which is 2.
Mhm.
Nice. Maybe we can try to find f of 3. f of 3. So oh yeah, actually, another, yeah, go on.
So like I was thinking if it like this it is in two variables A and B. If like in the
Yeah,
like the Cauchy thing we take it to the n variables, then we can quite easily prove that f of p is equal to p. And after that I think it won't be that difficult.
right. So that's okay. So there's a small problem with that actually. So we have f of a plus f of b has the same number of divisors as a plus b. So yes, you might be saying that you're saying that you can substitute b equals b plus c, I guess. So if we substitute b as b plus c, we have f of a plus this, a plus b plus c. The thing is, I can't say that then this is has the same number of divisors as f of a plus f of b plus f of c. I can't just put this as f of, sorry, I can't just put this as b plus c. Wait, actually, I should like because this is adding up to, like for example, for example, f of 3, uh, wait, no,
Like I get it that
wait,
it is a problem. I was thinking if we can find a manipulation or some idea so we can show the
yeah.
similarity.
Actually, the problem is that when you add stuff, a plus b plus c, then you can do something like this is equal to a plus b plus c. Like having equal number of divisors is not this is sort of weirder than equality. So that would need some extra gatekeeping, but maybe it is possible. Oh, also, another useful theorem uh, called Bertrand's postulate. It's quite simple. It's just that between any n and 2n, there lies a prime. Right. So for all n, there is this prime p such that p belongs to n comma 2n. So for example, if n equals 3, sorry, actually, I don't know if it's no, if n equals 3, then p can be 3 or 5. There are two primes in this range. If n is 4, then in this range there are 5, 7, two primes again. So yeah, I think so. Like, there's a solution without this postulate, but my solution does use this. Not sure. What do you want to see? The question. Oh, yeah, let's try and find what f of 3 is. So like this time we have some more equations. We have f of 3 plus f of 1 is has the same number of divisors as 3 plus 1 equals 4. And we also have, and this is just f of 3 plus 1, right? Because f1 is 1. And then we have f of 3 plus f of 2, which is 2, has the same number of divisors as 3 plus 2, which is 5. And then we have f of 3 plus f of 3 equals 2f of 3, has the same number of divisors as 3 plus 3 equals yeah. So now if we break this into cases, this has 3 divisors. This d of 4 is 3. So this has to be of the form p square. This is a prime. So this has only 2 divisors and only primes have 2 divisors. So this has to be of the form some prime q. This it has 4 divisors. So there are two choices. It can either be sorry, q or rs for primes rs. So yeah, uh,
I think f of primes are primes.
f of primes are primes. Hmm, interesting. Do you have a proof for that or you're conjecturing?
No, no, I have a. It's like
Sorry?
the same. It's like basically A equals B equals P.
Acha. Yeah, what do you do?
Yeah, you just put A equals B equals P and you're done by a divisor argument.
Really?
2f of P is similar to 2P. And then f of P must be some prime. Like,
Same number of divisors.
wait, f of P is either some prime or 4.
Oh, interesting. Yeah.
Oh, I forgot the case of 4. I just
No problem.
realized it.
This has 4 divisors. So it can either be RQ or RS. Wait, actually, we're not done, right?
Why?
We just have f of p is a prime.
Yeah, I never said it's P. I just said like some prime.
That's good. That's right.
Or
Nice. So we have
4,
f of
but I
3
don't know how to
or
deal.
5 or 4. But that is not much of a problem because note that f is increasing.
It's weakly increasing,
So
right? It's strictly.
yeah, it's increasing. Same. Weekly increasing. So uh, there need to be a lot of force in the starting, all fours in the starting, and then some primes.
Yeah, I guess if we just saw like f of 5 is 5, someone said it in the chat,
Exactly.
then,
Yeah, exactly.
then we have dealt with that.
Yeah, we can check the issue of 5 is 5. I'm not sure how you got a 5 equals 5, but it was a bit tedious last one. Wait, so let's complete f of 3 ones. F of 3 plus 2 is 2. Yeah, so we have f of 3 plus 2 as prime. Now, note that q has to be greater than 2. So it's odd. And f of 3 plus 2 uh, is congruent to f of 3. Has the same parity as f of 3 mod 2. So f of 3 is odd. So f of 3 is odd. Like, can we try to generalize this? Can we try to conjecture that f of odd is odd and f of even is even? The reason this will be really nice is that it essentially gives us strictly ingredient. So yeah, we want to try to prove this. Can we prove this? Also, did people get why this implies strictly increasing?
Yeah.
Yeah, because like if we have some consecutive numbers, one is even, another is odd. If this gives an even when taken when f of even is if f of even is even and f of odd is odd, then these two can't be equal. Yeah. So wait. So again, how did we get f of 3 is odd? We got it because we found that 5 is a prime. Hence, f of 3 plus 2 is a prime, and hence f of 3 is odd. I think there was something, there's something similar in f of 2 also. We got, actually in f of 2 we did directly, but we can also do f of 2 plus f of 1 equals f of 2 plus 1 is similar to 2 plus 1 equals 3, which is a prime. So f of 2 plus 1 is a prime. So f of
Oh,
2 is even.
wait. So, like, we can use Bertrand's postulate here, right? So,
Exactly.
yeah, like we can just
Uh,
add, we can just add like an extra, like, I mean, what do you call it? You just take f of k, and then there must exist some value less than k, like say j, which you can add to it to make it a prime. So, like, if it's odd, then the value you add must be even. And then if it's even,
yeah,
the value you add must be odd. So, like, by parity.
exactly. That's the correct idea. I'll just state what she said. Uh, yeah, so she said that if we have f of k, and we know that there's a prime p, which is greater than equal to k, no, which is actually the thing can be strengthened to greater than k and lesser equal to 2k. In fact, it has to be less than 2k because it's not even, obviously. Right. So we choose such a prime, we find such a prime p, and we know that f of k plus f of t minus k e- equals is similar to, sorry, k plus p minus k, which is p. Now we can induct and we assume that uh, we can strong induct and we can assume that f of 1 dot f of k minus 1 are all equal to 1, 2 k minus 1. They are all identity, right? We now know that p minus k is at most 2k minus k, which is k. So this term is less than k. Sorry, this term is less than k. Hence, f of p minus k is p minus k by the induction hypothesis. Is this clear why f of p minus k is p minus k?
Wait, how did we get it exactly that?
Yeah. So basically, we know that p minus k is less than 2k minus k, which is k.
Yeah.
Yeah.
Wait,
And
one second.
less than k, we had strongly inducted and assumed that f of 1 is 1, f of 2 is 2,
Uh,
f of k minus 1 is k minus 1.
Hmm.
So does we know that f of p minus k is p minus?
Also, we're done. Right.
Uh, Not yet. And yeah, we are done with strictly increasing. Why? Because we know that f of k
No, you
plus
got equality, right? It's p minus k is p minus.
indeed this is by induction hypothesis.
Hmm.
We need to prove that f of k is k.
Oh, okay. Right. My bad.
Wait, actually, I think I should probably write it down nicely. Uh,
Yeah, I got my mistake. Yeah, I see what you mean.
yeah, I'll just write it down for clarity's sake. So here strong inducting on Q. We assume f of 1, f of 2, f of k minus 1 are all identity. Then we choose a prime p which is greater than k and less than 2k, which we can do by Burton's. Then we have that f of k plus f of p minus k is similar to k plus p minus k, which is p. It has the same number of divisors as p, but number of divisors of p is exactly 2. Hence, f of k plus f of p minus k is nothing but a prime. However, p minus k is less than 2k minus k by this inequality, which is k. And hence, f of p minus k is p minus k because we by the induction hypothesis. Then we have that f of k plus p minus k is a prime, so it's odd. Now, if k is even, if 2 divides k, then 2 does not divide p minus k. P minus k is odd. And since this plus this is odd, this has to be even. Does this make sense? And if 2 does not divide k, then 2 divides p minus k since p is odd. And we have that this is even, and since the sum is odd, this must be odd. So f of k is odd. And we have proved that if that f of odd is odd and f of even is even. Is there any part of the proof that I should explain again? Okay, great. So yes, strictly correct. F is strictly increasing.
So, like, after this deduction, can't we just say that it is not weakly increasing now, it's strongly increasing?
Exactly. Correct. Strictly increasing.
So, now this is really helpful.
Yeah, it's quite strong. In fact, like, okay, does anyone have an idea of what to do forward? We want to show f as identity. F of x equals x.
I think I have an idea. Uh,
Yeah. Well,
like I don't know if it works. Like so basically, yeah. So basically, if you don't have identity, then like for some k you must have that like f of k is like greater than or equal to like k plus two. So then the value after that
greater
also must be like that.
greater or equal to k plus 1, right?
Oh yeah. Wait, but then we have it that like f of an even number must be even or something,
Yes,
right?
so you're assuming, uh, wait, so are you assuming k to be even?
Yeah, like I mean, if it's the same parity, right? Like f of k is the same parity as k, right?
Oh, yeah, actually, you're right. Yeah, you're right. So k plus 2. So, wait, I'll just explain. We can't have f of k to be k plus 1 because these two have opposite parity. So, we can
Yeah.
still move along. Yeah, so then,
Yeah. Wait, actually, one sec. I think I made a mistake.
actually,
So can we prove like that f of f is surjective
f
or
is
sorry
surjective.
injective like injective I mean to say.
Injectivity strictly increasing means that if a not equal to b, like we can assume a is greater than b without loss of generality, right? But then we know that f of a is greater than f of b,
Oh yeah, I
and f of
meant like
a not equal to b.
onto I meant whatever it
Sorry,
is. I meant onto whatever it is, subjective or injective. Onto.
you mean f takes all values? The two values
Yeah.
can't take the same.
Fx takes all values.
That is subjectivity. Okay, so like injectivity is this is f of a equals f of b implies a equals b. This is what injectivity is. मतलब two values can't take the same value under f. That is injectivity. And subjectivity is that f takes all values. Yeah, so you're saying we want to prove f is subjective. Interesting. Uh, Actually, if you prove subjectivity, will be done, right? Yeah, if you prove subjectivity, you'll be done because it's strictly increasing. So if it takes all values, they have to be strict. If it takes one, two, three, four, five, dot dot. So this has to be f of one. This has to be f of two
Can we
because
induct
they
for
are all.
subjectivity?
Can we induct for subjectivity?
Like, consider
Yeah,
the
we can
smallest value
induct
not
for
taken.
subjectivity. Acha, interesting. So so let's induct. Sure. We say that f of one, f of two, f of k minus one are all identical. Now we are using that let a be the smallest value not taken. A smallest.
Yeah, so f of x equals
Not taken. Now what f of so so a is clearly greater than k minus one and
In fact, A has to be
so
like yeah, like K has
it
to
has to
be
be k,
A
right?
because then we can just
Correct,
say
correct.
K
So A
minus 1.
has to be k. Exactly. So we have f of k must be greater than k. But like this is equivalent to just normally nothing. So if for the sake of contradiction, suppose f of x is sorry, f of k is greater than k. Or like we have lower bounds everywhere. We want some sort of upper bound. Like maybe try and see that if we can find the particular value at some, like maybe we can say that f of 1001 is 1001. If we know this, then we can automatically say that for all f of a equals a for all a less or equal to 1001. Do you see why? It's because
Yes, it's
f is
strictly
strictly.
increasing.
Yeah, yeah.
Like using this idea, we can just prove f of p equal to p and we'll be done.
If we could do that, but you remember over here we proved that f of p is a prime. We didn't prove which is p. Wait, where's that? Uh, yeah, we've proven that f of p is some prime. If we could prove that this is p, then we'd be happy. In fact, like, okay, wait. So first of all, did people get why this will imply this? It's because f of 1, f of 2, this is greater than this is greater than f of 3, f of 1001, which is 1001, and this is 1. So there are 1001 values, distinct values between 1 and 1001. So all of them have to be 1, 2, 3, so on. Is there any doubt in this? Okay. So, but the problem with this is that, okay, f of 1001 is 1000, sure. But then after that, f of 1002 might be some random value, 1013 or something. So we want such checks to be periodic. Like maybe if we can get f of 1001 is 1001, then we might have that f of 2002 is 2002. Then we know that all values between this and this are identity. And if we could have this for infinitely many values, like f of 3003 is 3003, and so on, then we'll be happy. We'll be done. So can we think of some infinite sequence of whose f values we? I'll just write down the question again. We have f
Powers
of
of 2.
a plus. Okay, interesting. Like again, powers of two is a really nice idea because a plus b. If you have 2 raised to n plus 2 raised to n, that is 2 raised to n plus 1. So it's really nice. You know the number of layers of this. Let's try this out. We get f of 2 raised to n plus f of 2 raised to n equals to f of 2 raised to n. This has the same number of divisors as 2 raised to n plus 2 raised to n
Oh, wait, powers
raised to
of 2,
n.
which are like n is prime plus 1 or something like that. N is prime minus 1, something like that.
Okay, let's try to find what values of n are nice.
Yeah.
So we have that 2 f of 2 raised to n equals 2 raised it has the same number of divisors as 2 raised to n plus 1. Now, what is p of 2 raised
We
to
are
n plus 1? What
assuming
are the
a
number of
and b
divisors
to
of
be n. So
2
if
raised to n?
we assume like just n to be, I guess, odd, then we can just say that,
N equals p
sorry,
minus 2 is quite
n
nice.
to be even, we can just say that f of 2 to the n is some 2 into perfect square.
But again, perfect square is sort of vague, right? Wait, let's
It is
just find
now
what.
immediate, right?
Sorry.
It is now immediate, right? We can just take n to be p minus 2, and
Yeah.
therefore number of devices turns out to be p. So it can
Yes.
only be 2 to the power like k to the power p minus 1, but by like strictly increasing condition we
Wait, no. How do you resolve that it's not some other power?
Wait, I'll tell you.
like we have
So what you said
strictly
was,
increasing k to the power.
Oh, yeah, 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 yeah. We are done.
this is what you were saying, right? You put n equals p minus 2, and this becomes d of 2 raised to p minus 1, which is p. And
Yeah.
hence, we need d of 2 into f of 2 raised to n to be some prime. That means this has to be of the form some q prime raised to p minus 1. That is the only possibility. And since this is 2 into f of 2 raised to p minus 2, we have that
Yeah,
2 is q. So f of 2 raised to p minus 2. Wait, what did I mess up? I didn't mess up. It's 2 raised to p minus 1 by 2, which is 2 raised to p minus 2. Very nice. The p minus idea was very nice. And now, do you see the finish? We're done.
Yeah,
Basically,
like we are
we
done
say
with
that
this, I guess.
f of 2 raised to 5 minus 2 equals f of 8 is 8. We know that f of 2 raised to 7 minus 2 equals f of 32 is 32. And we know infinitely many number of values. So this decides all values, the value of all f of a equals. Should I repeat any part of the proof? Oh, I think I'll just go over the entire proof briefly first. It was yeah. So uh, yeah. So we had this condition. We did not have strict increasing. So what we first tried was to get strict increase because we first tried to get strict increasing. To get that, we use Morton's postulate, which says that between n and 2n, where actually it's a strong bound at n. So basically, there exists a prime p which is greater than n and less than 2n. So we used that to prove strictly increasing by saying that if we can prove f of odd is odd and f of even is even, then we'll be done. We'll have strictly increasing because f of even will be even and f of even plus 1, which is odd, will be odd. So these two can't be equal. After that, we used that, say, f of, we consider some k and we say that we strong induct by saying that f of 1, f of 2, f of 3, dot, dot, f of k minus 1 are all 1, 2, 3, dot, dot, k minus 1. They are all identity. Then we have that f of k plus f of p minus k, where we chose p to be between k and 2k, have the same number of divisors as k plus p minus k, which is t. The number of divisors of p is just 2. So this part, all of this, has no other choice than to be a prime. Since it has to be a prime, and we know that f of p minus k is less than 2k minus k. Since p is less than 2k. So p minus k is lesser equal to, is strictly less than k. So this part becomes f of p minus k is p minus k, because we know that like p minus k comes somewhere over here. Yeah, so we know this.
I
Shall you go on?
I have a doubt. So, like in the strong
Yeah.
induction part where we proved that they have same parity, we first assumed that 1 till k minus 1 all are the identity, but let's say, but like in the proof, like for k we proved that k just has the parity same with f of k, then we cannot proceed on to k plus 1, right?
No, we can.
Wait. Okay,
Because
so
now k plus 1 is not the identity, like f of k plus 1 is not k plus 1, like we haven't proved that.
yes. No. So okay. So actually, you're right. We can weaken this assumption. We can say
That it has the
f of
same parity.
exactly. Yeah. Sorry, actually, this is my bad. All of them have same parity. That is, f of a is congruent to a mod 2. Yeah, my bad. Then I think we can do this, right?
Yeah, I
Yeah,
guess.
we can say that f of k plus f of p minus k uh, is definitely a prime, which is odd, and f of p minus k, f of t minus k is congruent to t minus k mod 2. Then prime minus some odd minus t minus k will be the opposite of t minus k, which will be something like uh, if p minus k is odd, then it will be even. So f of k, so if p minus k is odd, then f of k has to be even because f of p minus k will be odd, and then we'll be done. I think this part is clear.
Uh, I also have a doubt. Uh,
Yeah.
so like must there exist like a p minus k then such that like f of p minus k equals p minus k? Uh,
Must there exist? And we prove that eventually, but in this until now we haven't proved it.
I mean, we're using that, right?
Yeah. Wait. Actually, let me explain this proof again. Yeah. So we are strong inducting on the assumption that f of a is congruent to a mod t for all a lesser equal to k minus 1. And then we are just saying that f of k plus f of t minus k
You mean mod 2?
must, yeah, sorry, what was that? Thanks. Must be a prime, which is odd. Now case 1, if k is even, then f of t minus k, sorry, then t minus k is odd, right? Because p is odd. Hence, f of t minus k is odd. Hence, since this part is odd and this part is odd, we have that this is even. Is this part of the proof sound?
Oh yeah. Got it. Thank you.
And then k is odd follows similarly. Like, if k is odd, then this will be even. This part is odd, so this has to be odd. Yeah, the strong induction catch was good. So like, yeah, should I continue with the part of the proof or should I explain something in this proof? Okay. Okay, I'll just finish explaining the proof. Yeah, so we use that thing to get that if it's strictly increasing. Then we remark that if we inducted on k minus 1 again, and sorry, we proved that we found that f of 2 raised to n plus f of 2 raised to n is 2 into f of 2 raised to n has the same number of prime factors as 2 raised to n plus 1. And if n is p minus 2, if n happens to be p minus 2, we have 2f of 2 raised to p minus 2 have the same number of prime factors as 2 raised to p minus 1. And number of prime factors of this is nothing but p. So this part has to be some q raised to p minus 1. But since this part is even, q has to be 2. Hence, f of 2 raised to p minus 2 is 2 raised to p minus 1 by 2, which is 2 raised to p minus 2. So now we have f at infinitely many points. And then we remark that we know that f of 32 is 32. We know that f of 2 raised to 11 minus 2 is 2, sorry, 2 raised to 11, f of 2 raised to 11 minus 2 is 2 raised to 11 minus 2, and so on. And since f is strictly increasing, and all of them have to be identical. Is this last part clear?
Yeah.
Oh, great. I think we're out of time then. I'll just put the next question. I'll just put the next question and then I'll give you some time soon. Okay, I don't have to write it down. Yeah, just check out India TST day 2 P2. That finds the
Can
whole
you
solution.
Which year? Year?
Uh, India, wait. I'm not able to verify some reason.
Year.
can you write it in chat?
India TST 2023 day 2 P2. I'm not sure if it's day 2. It's some day ka P2, but 2023 P2 definitely. Another good one is India TST 2023 day 3 P1, I think. I'll send both these problems in this one. Wait, I think I can post. Oh yeah, nice. Yeah, here is this is the problem. And this is the P1. So, yeah, I think that's it for the class. Is there any doubt in anything that I covered? Okay, then I think I'll stop sharing.